So again, I apologize for not being here yesterday, and I hope that you had a relatively productive day. I want to wish you a very happy National Oatmeal Day today. It was very apropos, given that it was all snowy out this morning, kind of, that preparing for winter kind of situation. Today, our plan is, given what we did yesterday, or what I believe you did yesterday, we're going to start with a warm-up problem. We're going to go over any of the workbook pages that you would like to go over, given where you were yesterday, and any homework problems as needed, and then work on the apply problem that you haven't seen yet, but we'll get to today as well. The plan is to do a Unit 2 test tomorrow. That was the plan. It's kind of been the plan the whole time through. We're pushing it back by a day because of my absence yesterday. So if you have questions, today's the time. You're also welcome to come and hang out with me before school tomorrow or whatever. If you need other things, you can also come in during Liberty Time today. Whatever works for you is great for me. Okay? Questions before we jump in and get started? All right. So I'm going to put a warm-up problem up here for you to take a look at. I'll give you just a couple minutes to look at this, think about it, write down some answers, and then we will discuss. Sound good? All right. All right. Here we go. You want to show me some answers? Show me some answers. If you don't have, it's okay. What's your vote? What are your votes, friends? No idea is a bad answer. A, B, C, D. All the same.
Yes.
Other votes? It doesn't have to be on a whiteboard. Jason, what was your vote back there? Did you guys come up with something? Same as them? All the same? Chris, what did you guys come up with? All the same? Lucy, what does your board say? Oh, okay. More important questions. All right. So talk to me. Where do you get the answer you get?
So we're going to say in a raw kind of light.
We'll get started.
Yeah, sure. So FNet equals MA.
Okay, hold on. Let me write that down because that's important. FNet equals MA. Does everybody agree with that?
Yes.
That position. We got to start somewhere. Okay.
But A isn't really a factor because they're all moving at the same speed.
Okay, so they're all moving at the same speed. So the acceleration is 0. Does everybody agree with that?
Yes.
Okay. All right. Now what?
So, shoot, this thing fell apart.
No, we're learning together, right?
I was thinking like proportionality.
Mhm.
Like as the mass increase, FNet increases because A isn't changing.
Okay.
So that's what I was thinking.
So let me reiterate what you were saying, Elizabeth. So if A was a value,
Yeah.
let's say A was 3.
Mm-hmm.
Pick a number, right? Then the net force would be proportional to the mass, right?
Mm-hmm.
The more mass, the more force would be necessary. That's correct, assuming that A is a value.
Darn it.
But, so all we're doing is learning together, right? And that's what we're here for, so that's great. So in this case, what you said is that A is equal to 0, so that means MA equals 0, which means FNet equals 0, which means that the net force on any one of these things needs to be 0. Okay, now what?
So that means. No. Okay. Well, if you look at like pod A, its FNet has to be 0.
Yep.
So that means like both rod A and rod B have to be the same, so that they cancel out.
Okay, so
do that for every single pod.
So FA and FB. So FB has to be equal to FA. Okay, so now.
Oh yeah, that makes sense. Okay.
So what? You guys all took a step in one direction, but I missed the step.
So then B is equal to C.
C and C is equal to D. And A is equal to C. Yeah, it's all.
So they're all the same.
Yeah, they're all the same.
But what?
No, I'm 0 because those forces have to cancel out.
Okay, so.
Look at pod D, friends. How many forces are acting on pod D?
Yeah, so that's what I was like.
So let us into your brain, Jacob.
Oh, I don't know.
No, you know.
Wait, is it D is greater than A is equal to B is equal to C?
Well, let's okay. So what do we know about D?
So it's non-zero.
Has to be what?
It has to equal zero, because if F net on every one is zero, then, and there's only one, then D has to equal zero.
So FD, if the net force on pod D has to be zero, then FD has to be zero. And if FD is the same as
So
FC,
they're all zero.
then this has to be equal to zero, which means this. Yeah. So what's the answer?
All zero.
There is no tension. Once they've accelerated to whatever speed they're at, there is no tension.
So there's only tension if there's acceleration.
Correct.
That's crazy.
Wait, for
That-
but like if
As long as the net force is zero.
I have a question.
Okay.
Like it makes logistical, like mathematically makes sense.
Yeah.
Like in my head.
From like a theoretical point of
Yeah.
view, but from a okay.
my overthinking.
I have a hypothetical question.
Hypothetical
So
question,
if
go.
there's, like, imagine this happening in space.
I am.
This thing pulling on it, and then, like, if the ship stopped accelerating and it had a constant velocity, wouldn't the stuff behind it catch up? Like,
the pressure is still moving.
So as long as everything's moving at a constant speed.
never mind. I was thinking like, yeah, I know what I was thinking.
Wait, okay, I
So
understand it now.
so if the ship starts moving, like and is accelerating, then that means that it's going to have to apply a force to FA to get all the rest of the stuff to move and to accelerate, right? Not just move, but to accelerate. Or if the ship decides it needs to stop, it puts on the brakes, right? Then that's going to apply a force this way that's going to cause all of those to have a force as well, right? If it's a rod as opposed to like a string. If it's just a string and this one puts on the brakes, then everything's just going to crunch up into it, right? But as long as there are all these like, static rods, then it would just kind of, yeah. Is that okay?
Can we do like a hypothetical, like if it was accelerating, how you would calculate it?
For sure. Let's do it right now.
Could you also view this whole thing as a system and just assume that it's zero since it's all moving at a constant velocity?
Sure. Now,
Give me a reason.
we will so the trouble with that is that that these are all internal forces, these A, B, C, D, E forces or whatever are all internal, so you can't really see them without knowing
Okay.
what's going on. Does that make sense? But if you look at them each individually, knowing that it's not accelerating, then you can say that. Because you have to look at, like, in order to get to zero, we had to really look at pod D all by itself, right? Yeah. So let's play the game quick, because why not? That's what we're here to do, right?
We just had an acceleration plan.
Yeah, so let's say the acceleration is 1 meter per second squared. If that's the case, can you figure out the tension in each of those rods? Sure, of course you can. Do you want me to give you a moment to do that? Fantastic, go ahead. What's that? Yeah, so I want to know the force. So play the game with me. If it's accelerating, what? A is greater than B is greater than C is greater than D. Did you have to take the masses into account?
Kind of, but not really. I mean, I didn't like calculate it out exactly, but you can just look and see that A is going to have more mass because it includes B, C, and D,
Yeah,
and B only includes B, C, D, and C.
yeah. Did you guys catch what she said? She said it really fast.
Oh, sorry.
No, it's fine. I just want to make sure that everybody else heard that, right? So A has to pull all of this mass. It doesn't really matter how big it is, right? And A and B have to pull just this mass, so the mass is smaller. The total mass is smaller. So yeah, sweet. Nice job, team. Cool. Yay for us for learning things. It's a beautiful thing. All right. Yesterday with Mrs. Gribble, you worked through some workbook questions, which you may or may not still have questions over. I know that you went over 2J. Did you guys have any questions about that one that you'd like to ask me? Or are you feeling okay?
Yes, is the force of tension greater
We
than the
already
force of
said
friction
this
or not?
answer.
I thought we already went over it.
I think you did. I just want to make sure that there weren't any.
We did, because we were on that for a good 10 minutes.
It was
Wow.
1:15.
Yeah,
That's
it
why
was-
I-
Okay.
I did not expect the subs to jump in like he did.
Oh, yeah. They were kind of like, he was interjecting
No,
and she
and
was
then
trying
he
to
told me
teach, and then
later
they
in French
could like,
today
Oh dear.
they couldn't, yeah, it didn't go well.
Fair enough. All right, let's keep going. So how about 2K? Were we okay with 2K? Yeah? And then you did 2F. This is the bulldozer problem. Did you guys make it through this one?
Yeah, and we were like,
I just
yeah,
had,
and
like,
she
started
explained
working
like
on it.
friction. I was like opposing.
Yeah,
Or it's like the opposite direction
Going
because
with the most-
It's weird, right? So here's the thing. It's kind of a hard thing to get your head around, but it's super true, right? So the way we always think about friction is that friction opposes motion, right? I told you that for a million years. But that's only true when we're talking about something like sliding, right? So if I take an object and I slide it, the friction is going to go backwards. In the case of something moving, like rolling on wheels or like us walking, the friction actually is what allows us to propel ourselves forward. So this is something that's really important to think about now that it's getting colder and icy and all of that sort of thing. If you go out and you try to walk, let me just say this real quick and then I'll answer your question. Is that fair? If I go out and I try to walk on a super icy surface where the coefficient of friction is 0, and I try to walk, I don't know if you've ever tried this, what happens to you?
You slip and fall.
You slip and fall, and it's because the friction that actually helps propel you forward does not exist. So the friction, the thing that makes me, like, allows me to do this, isn't there. Okay, you with me there? So the friction is actually what's pushing me forward. It doesn't seem like that, but that's what's happening when you've got something where you're actually using friction to move. Okay, which is what's happening in the bulldozer example as well. And I don't want you to get like too wrapped up in this because most of the time when we're talking about friction, it's about sliding, okay? In which case it is going to oppose motion. But in this case, if you draw the free body diagram of the bulldozer, right? So you've got the force of gravity going down. And I don't know if she went through this part, but you want to make sure that these two arrows are the same length, like count the boxes same length. And if you don't trust yourself to count or you want to make sure it's very, very clear, then you can also write FN and FG are the same length. Like if you do that explicitly, then anybody who's grading your test will know that you know the physics, even if you don't know how to count. Okay, because counting is like a first grade skill and physics is a, like 11th or 12th grade skill. That's the thing that we really care about. Okay, so you know those things. You know that the block is pushing this way, right? Because the bulldozer is pushing on the block is pushing on the bulldozer. So there's got to be something driving it this way. You could talk about that as the engine, but really the engine is driving the wheels, and it's the friction between the wheels and the ground, or the treads and the ground, that's pushing it forward. Does that make sense? Let me say one other thing real quick. I'm sorry, Garrett, I'm not trying to ignore your question, but I just want to say, if on a problem like this, you just said it was the engine that was pushing you forward, as long as nowhere in the problem did it talk about friction in that way, I think it would be okay. All right, go.
So you have to consider the bulldozer as a system.
Well, this question asks you to consider the bulldozer by itself and the block by itself, and then the bulldozer and block together. Does that make sense? That's what the question asks
But I
you to
mean,
do.
like the friction on the tread, that would be like one part of the bulldozer system, and since the friction is going this way, but the system is still moving forward.
Say that.
He's thinking like the free body diagram, just the tread.
Oh, got you. Yes, so I'm thinking about the bulldozer as a whole, as a thing.
Okay.
Yes, and the tread is part of the bulldozer. Yes. Does that answer your question, hon?
Yeah.
Okay, go.
And like the sub gave us like the notes to read.
Yes.
Really quick, and it said something about like the Earth is pushing back.
So the Earth is the surface. That's the friction that we're talking about. Yes. So we're going to get into the. I'm sorry, I keep interrupting you. Speak. So we're going to get into like the Earth pushing on the bulldozer pushing on the Earth. That part, that's coming in the next unit. So we'll really get into that and dig in it, and I think it'll make more sense. I teach this out of order from what AP says because to me it makes more sense to do this first and then do those internal forces next. It is more logical as a teacher to me to do it that way.
So would there be friction going like forward and backward?
No.
Or just
It's
backward?
in this case the friction is actually pushing in this direction. What they're calling the friction. Yes, this is the force of the block
Oh wait.
on the
So
bulldozer.
is there like a force of the engine on here? Or
No, that's what I would call that's what they're calling the frictional
no?
force.
Oh.
Mhm.
Okay.
Yeah, so you can call it the engine or the friction. They're choosing to call it the friction for other things later. Yeah, does that make sense? Does that help to make that kind of tie up a little bit neater? Yeah, it's a little confusing. I agree. Anything else on this one that you want to go through?
Of this paper.
So like,
on this question.
if the block wasn't pushing on that, wouldn't that show that like it would just keep sliding, like even force stopped? Like there was, so like, you know how it shows that the block is pushing against it to the left?
Mm-hmm.
So like, if it wasn't pushing a block, would that just show that it couldn't just keep sliding?
No, so this friction, it's a little bit, it's different from sliding friction, which is the thing that we usually talk about, because this is kind of like, it's not rolling friction, but it's kind of, so it's because there is friction, those treads are able to move the bulldozer forward. If it was on ice as opposed to in mud, then it wouldn't be able to roll. Like physically, this thing wouldn't be able to roll. Kind of like if your car is stuck right in like on an icy patch and you put the gas on, it just it spins. Same thing, because there's no friction to allow that motion to happen. Is that okay? We'll talk a little bit more about rolling friction in a few units as well. Yeah. So this is kind of like a preview of things to come. Woo. Yeah. Other questions on this one? And you guys finished the rest of this problem, right? Okay. And then did you make it through the mouse problem or no? You what? On your own, but we didn't discuss it? Okay, let's do it real quick then, shall we? Okay, so free body diagram for this one. So I really hope that mouse was involved, but it really isn't. It's just a little crate on an axis. Yeah, do what you need to do. Yeah. What forces do you have acting? Gravity, the force of the earth. Which way does that one pull?
It was going towards the center of the earth. That's first.
On the box or the crate or the whatever it's called, FG. What else you got?
We've got the normal force, which is perpendicular to the
Yes, and super important that does not push straight up, friends. It does not push straight up. It has to go perpendicular to that surface, right? So double check yours, check your picture, make sure that it's not going straight up and down, because that would be wrong, okay? Perpendicular, so that's the force of the surface on the box. That's Fn. Normal means perpendicular to. And then you've got one other force. What is it?
friction.
Frictional force. Yep. So this is the force of the surface on the box. FF. If you were asked to draw a free body diagram on a test or a quiz or on a test in May, these are the three forces, no more, no less, okay, that you would want to have. Don't break it down into components on that free body diagram. They will say, wrong. It's sad, but just don't do it, okay? All right. So part B asks you to find the sum of the forces. They call it the y direction. That really makes me, like, my stomach hurts when I read that because it doesn't make sense to me. Why? Because if that angle is more than 45 degrees, then the y and the x kind of switch positions. So instead of calling it the y direction, I think really what they mean is what? The perpendicular direction, right? So I'm going to change that right now so I don't get confused, because I don't like it when they do that. So perpendicular direction. So I'm looking at the things that are perpendicular. So now I'm going to go against everything that I said. I'm not using this as my free body diagram anymore because I'm going to break it down into pieces, right? So I'm going to break my FG into pieces. One goes this way. This is FG perpendicular. Perpendicular. And the other one is going to be FG parallel. In this case, we really don't care about that one, but we'll call it good anyway. So I've got FN and FG perpendicular that are going to add up to what? 0, right? So Fn plus Fg perpendicular equals MA perpendicular. This is the net force in the perpendicular direction. Okay, so you can write that in a lot of different ways. So that's kind of what they wanted you to write here. And then what do you know about the acceleration? Oh. Not accelerating. So we know that that's 0. This one's in the positive direction. This one's in the negative direction. So that means that we can write it as Fn is going to be equal to Fg perpendicular. Hey, what's Fg perpendicular equal to in terms of that theta? How are we doing? Is that okay? So I'm not really writing out my reasoning. I can read to you what they said for the reasoning. You ready? Here it comes. Since the box would accelerate down the incline, if it were to accelerate, we choose our axis down the incline and perpendicular to the incline so that we find the components of the gravitational force, since it's the only force that's not parallel or perpendicular to the incline. That means we're going to break it into pieces. Okay? Then what I'm going to call perpendicular direction, the two forces of the normal force and the component of the gravitational force, since it's not accelerating, those add up to 0. Okay? That's what this is showing me here. That's the physics that I need to see. And then we can say that we can break that into mg or fg cosine theta. That's really what they want to see here. I'm going to go to the back because this is the more fun part.
Yeah, this was the part.
What did you say?
Was that the second box?
That was the second box, yeah.
I gotta erase this.
And then the third box, basically the way that they had it set up here is that this was the second box, and then this was the third box. Yeah. Go.
So if we did it, could you have done 2 different angles for that? Oh, shoot. Never mind.
Are you sure?
Yeah.
Okay.
Do we have to write words if we like write that? Like,
So I want you to know what the words are because sometimes on an AP question, it will ask you to write out your thinking. I'm not going to look at this, I'm not going to grade it, but I want you to be able to know that you can write down your words, right? So that if on a test or a quiz or in May, it asks you to write things down in words, you know how to do that. Does that make sense? The point of these is to start training you to do those skills that you'll need to do. Does that answer your question, Jacob? It was kind of a roundabout way to say I don't really care because we're talking about it. We're using words. They're just oral instead of written. So now we're going to do the fun part, the thing I like the most, right? Angela and Carlos perform an experiment. They get some stuff. They're going to use that to test the equation derived in part B. Hey, look at that stuff. We want to, dun-da-da, linearize the graph. Woohoo! So the equation that we wrote down, I'm just going to look up here, is Fn equals Fg cosine theta. I'm just going to write that down right here. Fn equals Fg cosine theta. If it says linearize, what does that mean? You want it to look like what?
Y equals mx plus b.
Woohoo! We love it. Okay. All you have to do is line it up, right? That's all you got to do. What's going to go on your x-axis? Cosine theta.
Yes.
Why? Because we don't want to have to deal with that cosine later. Because if you just put theta on that axis, then you have this cosine business. Blech, blech. Curves and yuck. And curves are not linear. We want something to be aligned, don't we? So that's what we're going to put on the x. What are we going to put on the y? Fn. Do you see how pretty this is? Yeah. And so then you're going to get this cute little line. And then the slope of that line is going to be what?
Wait, no.
Fg, the force of gravity. Yeah. Because the slope is the Fg part here, right? Because you haven't done it for a long time. I mean, you haven't been practicing a lot. The more you do it, the more you see it. Okay? Whenever you see the phrase linearize, all you have to do is like write y equals mx plus b above it and then line stuff up. That's all you got to do. Okay? Go.
So there shouldn't be like a y-intercept, right? Because there's no normal force. There's nothing pushing down on
Right.
it.
Exactly. So let's take that and run with it. So there shouldn't be a y-intercept, right? When I graph this data, so like that might be a question, right? So here's my stuff. Oh no, I got a y-intercept. What does that mean? That means that there was an error. It's a systematic error. It's an error that we screwed up for the whole thing. And it gave me a y-intercept that, oh my gosh, is negative. What is that telling me? It means that there's something else over here that's affecting my forces in the perpendicular direction. Right? And so then maybe you can brainstorm like what's going on, what might be acting, that kind of thing. Yeah. Yeah. But that would be the next step. That would be like part E, right?
It's a calculator error.
Not a calculator error.
Wait,
Human
so
error.
what would,
No, it would be like a systematic error. What's that?
what would the graph look like?
If there, it would just, the y-intercept would be 0. right? Because that's really plus 0. Yeah. Fair question. How are we doing, team? We okay? Fantastic. We're going to keep cruising. We've got a few minutes. Okay, so we're going to start this activity today. We may finish it on Thursday because tomorrow is going to be your test day, and I don't want to interrupt anything from that. But I really, really like this problem, and honestly, the most important part of this problem is the first half anyway. So here's the situation. I'm going to give you an applied problem and put you in groups in just a second. Okay? You have access to a metal track, a cart, a little mass hanger, one or more big whiteboards. They're way over there. Okay? And some slotted weights. So you're going to hang some weights over a string connected to a cart. Okay? I'm going to give you an angle. You're going to draw it out of a hat, really, or out of a basket. Okay? And your goal, using that pulley and triple beam balance and all of that, is to set up a track and determine the number of washers or the amount of mass necessary to hang here for the cart to be in equilibrium. We haven't really defined that word ever, but we've kind of been talking about it for a long time. Equilibrium means not accelerating. So that it's in equilibrium when the washers hang over this hang over on a string over the pulley. Does that make sense? So that's your game. That's your goal. Okay? We're going to get into some groups, and we're going to get started on this.
Do you have
By
decided
we're going to count off in just a second. Did you have a question? What'd you say?
Like that.
Yeah, like exactly like that, except that instead of a arm, it's going to be a pulley. But yes, same kind of idea. So the thing that I'm going to tell you is that was what? I had something to say. I don't remember what it was. I was with you. I heard you.